This is an example problem about determining the change in heat of a reaction using constant pressure calorimetry. A student decided to design an experiment to determine the enthalpy change of the reaction between hydrochloric acid and sodium hydroxide. She used the following apparatus. So this is an example of a coffee cup calorimeter. It's also considered constant pressure calorimetry because it's not pressurized. In other words, it's exposed to the atmosphere. So our pressure is going to be constant for our elevation. The student adds 100 milliliters of a 1 molar solution of an acid, hydrochloric acid, to a 100 milliliters of a 2 molar solution of sodium hydroxide. After mixing the solutions, the student observes the temperature of the solution rapidly rise, about 5 degrees Celsius. With time, the temperature very slowly drops back down to 24.2 degrees Celsius, which presumably is room temperature. Assuming that the coffee cup calorimeter is a closed system, complete the following heat transfer equation, and then using the experimental results of the students and the information below, solve for the heat of the reaction. We're given a specific heat capacity of the solution, a density of the solution, and we need to find the final volume of the solution. So what are our knowns? So we know we have these two volumes of acid and base, different molarities. We know what our initial temperature and our final temperatures were, as well as the difference between them, which is really what's key. We know the specific heat of the solution, and we know the density of the solution. What don't we know? We don't know the Q of the reaction, we don't know the mass of the solution, and we don't know the delta T of the solution, although we kind of do, just because I've said it's 5 degrees. So assuming it's a closed system, complete the following heat transfer equation. We've got this Q of the reaction plus Q of the solution equals some value. So the first law of thermodynamics states that energy is not created or destroyed, right? It can just be transferred and transformed. So in this example, a closed system, the energy is going to be constant. It's not going to be exchanged in and out of the system. So that means that if we add up the heat, the change in heat for the reaction and the solution, they should equal 0. In other words, you could rearrange that to say that the amount of heat gained by one is equivalent exactly to the amount of heat lost by another, and vice versa. So at this point, hopefully you can see the equation we're going to need to use to figure out the answer. So the equation is our easy to remember Q equals mcat. That's mc delta T. M, it's very important to note, is mass in this equation, not moles or molarity or something like that. C is our specific heat capacity, and delta T is our change in temperature. So we're given these values for specific heat and delta T. These values are only going to be good for the solution. You'll note in the subscript that we're finding the Q of the solution. Keep that in mind moving forward. So I've plugged in our knowns here. We know what the specific heat capacity is. We know what the change in temperature is. We don't know the mass of the solution. What were we given instead? How might we be able to find the mass? We were given a density of 1 gram per milliliter. Do we know the volume of the solution? We do. We were told it's 100 milliliters of acid and 100 milliliters of base. So the overall solution should be 200 milliliters. Since our conversion factor is just 1 gram per milliliter, it's also going to be 200 grams. So now we can plug all of these values in. You'll note when you're canceling units, you're going to get grams canceling. You might think that the K, which stands for Kelvin, and the C, which stands for Celsius, would not count, but you should note the difference between 29.2 and 24.2 Celsius is 5 degrees. Were you to convert those values into Kelvin and take the difference, it would also be 5 degrees. So either way, it's going to be a 5 degree change. So our grams will cancel, our units of temperature will cancel, and we'll be left with joules. We left this value of 4,184 joules. Students might make the mistake of stopping here. They might say, okay, there we go. That's our good number. We're done. But we weren't actually asked to find the Q of the solution. We were actually asked to find the Q of the reaction. And you'll recall from our initial calculation, using the first law of thermodynamics, the Q of the reaction is going to be equivalent to the negative Q of the solution. So that's our actual value, negative 4184 joules. This is a pretty straightforward problem using heat. You'll need to know the Q equals mc delta T equation. It is very common to not be given all of those values in a straightforward way. You might have to go about calculating it. So in this example, we had all of our values except for mass. We had to use density to convert to mass. Theoretically, you could be given maybe moles, and you would have to use molar mass to find mass at that point. A lot of different wrinkles could be thrown in here. I hope that this has been useful for you for problem solving and for how to approach problems about heat.